Hello students, this assignment is the last of the trio of binary trees exploration in which we conclude this set of assignments, and this assignment deals with making the maximum use, how to make the maximum use of binary search trees, which are trees that are kept in sorted order and provide us the efficiency which is far greater than a linear search. And this is precisely what this assignment is about, is how to maintain the binary tree so that the search tree, so that it does not get degraded or it does not lapse into becoming a linear search from a binary search. So one of the things that can happen over time to a binary tree is, let's say we start off with a tree that looks like this: 5, 2, 1, and then we have 7 and 6 and 9 and 10. Now I'm going to give levels to this. This is the root node. And so I'm going to say 1 is at level 2, 6 is at level 2, 9 is at level 2, and 10 is at level 3. The difference between the levels is at the most 1. So the maximum difference between any two nodes, right, any two leaf nodes is 1. And this makes this tree a balanced tree. So this tree is what we're going to call balanced. And if the tree were, if this had, if all the nodes were at level 3, or all the nodes were, if 10 was not there and all the nodes were at level 2, that would also be balanced. But this way is also balanced because the maximum difference can be 1. For a tree to be balanced, it does not mean that it has all the child nodes. You see, we are missing one of the nodes here. If we had 3, then this would have 2 children. So a balanced binary tree does not mean that every node has exactly 2 children, 0 or 2. It can have 1, it can have 0, it can have 2, but the difference between 2 leaf nodes at the most can be equal to 1, right? When we have a situation where, let's say, we delete node 1 and 2, and for some reason we delete 6, then what's happened is we've got a linear structure as opposed to a tree structure. And this degrades our efficiency of the tree. So what we need to do is, when we find ourselves in a situation where the difference between the heights of the leaf node, right, the difference between the heights of the leaf node is greater than 1, then we need to balance the tree, right? How to determine whether the difference does exist? Well, we need to have a way to find the depth of the tree or the height of the tree. And then the other thing we can do is, what is the actual depth of the tree and what is the calculated depth of the tree? For example, here I know that I've got 1, 2, 3, and 4 nodes. And I also know that for a binary situation, log to the base 2 of 4 is equal to 2. Therefore, the maximum number of levels that I ideally should have in this, the maximum height of the tree, it should be maybe structured like this: 5 and then 9 and 10, right? So this way I would have a height equal to 2, and that's what this number 2 indicates. So when I have, instead I have 1, 2, 3, the level is actually equal to 3, which means it's not balanced. If this is not equal to this, then the tree is not balanced, right? So now what I'm going to do is I'm going to try to balance the tree. Now, how am I going to balance it? One way, there are multiple ways of doing it. One way to do it is by deconstructing and reconstructing the tree. This is an expensive operation, but it does not need to be done that frequently, hopefully. And that's why it's important to keep an eye on the data and see what kind of data is coming in. But in any case, the way to do this is to create a vector in which we take all the nodes, right, traverse it in sorted order, and this is now a sorted vector. So there's no overhead to sort the vector. All we need to do is traverse the tree, which will be an order n operation, and store this inside the binary tree. Now what we are going to do is we're going to delete this and rebuild or reconstruct a tree. And how to do that? How to do that is precisely by, in a way that's very similar to the binary search process, find the middle. So this is the first, this is the last, and this is the middle. Find the middle node. The first middle node becomes the root of the tree, so 7 is the root of the tree. Then what we are going to do is we are going to go to the left side, right? And so this becomes the left for this partition. And this becomes the first for this partition. And then we're going to find the middle. The middle of this one becomes the left node of 7. So what we will have is we will have 5 becoming the left node of 7. And then the middle of this, which is 0, 1, 2, and 3. So 2 plus 3 divided by 2 is going to be equal to 2. So 9 is going to become the right node of 7, right? So we are done with this, and we are done with this. Now the new, so this first is going to merge here. The middle of, and the last is 10. So the middle is also going to be equal to 10. And then this is going to become the right node of. So every time the first moves over middle, you're dealing with the right node. Every time last moves, you're dealing with the left side. So we successively partition this array or this vector into smaller and smaller partitions by finding the midpoint and putting the midpoint as the successor node, either right or left successor of the parent node. So that's how we have rebuilt this tree so that now the tree is balanced. And that's exactly what we will be doing in this assignment. So I'm just going to show you the template here. So first we construct a tree with 13 nodes, print it, determine the height of the tree, find what the actual levels should be, and then go around deleting some of these nodes to make this tree unbalanced. After deletion, we determine the actual count. Now we know what it should be, the should be count, and then we go around and balance the tree, right? So we call the balance method. If the difference in the heights is greater than 1, we balance the tree, print the balanced tree, and then get the new height after balance just to make sure that it is what it is, and then we go ahead and delete the tree, right? So we are deleting this tree so that we can create another tree which has got a completely linear structure. So this is example number 1, and then this is example number 2, in which the tree is completely linear. And then you will see the height of this tree. The height of this tree, if you look at the output of the second tree, the height of this tree is 14, and the height of the tree should be 3. So we go ahead and balance the tree, and after balancing the tree, we find that the height is what it is, and it is not 15, right? So we take 2 trees and 2 examples to demonstrate balance. So what is our task here? So the binary tree ADT is the same from assignment 9, but what you're going to be doing here is a lot of methods have been given to you. The only method that you will be doing, you're given the balance method, but the helper methods of the balance method is what you are going to write. You are going to write the add to the vector method and rebuilding the tree method. And the add to vector method, the starter code has been given here along with the comments on how to build it. And then the rebuilding the tree, also some starter code has been given to you, and you need to complete the rebuilding the tree process, right? Okay.